Swayam Prabha. Digital India. Educated India.
Yeah, Srikant asked me to give you a short lecture on passivity. So what we will do is I will revise some concepts about passivity, the definitions and such, and then do something about on passivity-based control. This is the plan for part of the talk. I will speak about passivity in systems theory and also passivity-based control. And passivity-based control. That will be like the last, the second part of the talk. So, passivity, if you have studied stability in the sense of Lyapunov, passivity is some kind of dual of Lyapunov or complement. You have to leave behind the story about a model with a differential equation and so on. Passivity is really a black box perspective on system analysis, right? So, for instance, an electrical network transforms voltages into currents, a radiator transforms current into heat, etc., right? So, a falling object transforms gravitational force into speed of falling and so on. So, you have a system that has inputs and has outputs, and it transforms the inputs into outputs. So, let's look at passivity through the examples of electrical networks, because it kind of started that way. Basically, you have in an electrical network, you have this input here, a voltage that you apply to two terminals, and then you have a load, and you have this current flowing through the load. You can see that as a black box system, right? So you have the voltage that goes in and the current that goes out. You can say that there is a difference of potential that is here, right? And a difference of potential, as you know, is just the difference between two charges of opposite signs. And that will produce the current, right? So considering that the load is a conducting element, it will actually oppose probably to the passage of these currents. So owing to the laws of magnetism, the charge Q plus will, this is a convention, will move through the load towards the charge Q minus, and this movement of the charges is actually the current, right? So as we know, the current is the derivative of the charge with respect to time, how these charges essentially are moving inside the wire, so to say. In terms of energy, we say that there is an electrical potential energy that is transformed into kinetic energy, right? So again, we apply an input voltage, that's a potential energy that we have there, because we have some potential energy stored probably in a capacitor or in the adapter, and it is injected into the circuit, and it generates kinetic energy, it generates movement, meaning the charges are moving, there is this current that is being generated. So the key thing here is that there is a transformation of energy, right? So hence the dynamic system. Now, if we assume that the load is purely resistive, and we apply a voltage at the input, then we have what we are doing is we are supplying some energy into the system, right? So there is a supply of energy. This is an important keyword in passive systems. Naturally, the resistive element will warm up, right? So then some energy will be lost. So again, there is voltage, there is an energy transformation, there is current generated, it goes through the load, but some of the energy that is generated or transformed actually will dissipate in the form of heat, because the load is heating up. Then we speak of systems that are dissipating energy, right? So it's energy that is kind of lost. Well, not lost because, it's lost in the sense that you are not using it, but it is there, right? It's just transformed, and it's transformed in the form of heat. maybe you are too young to know the tungsten in the incandescent bulbs. Now they are all LEDs, but there was a time when they were resistive elements and they could get pretty hot. So that would be an example in which you have this energy loss, right? Another part of the energy maybe perhaps recovered for some purpose. Nowadays we see a lot of research, applied research into going in this direction. How can we recover energy from these type of systems? In France, for instance, they are working in Alstom, the company that makes trains. They are trying to figure out how to recover energy from the breakage of the trains. When they break, when they come to stop, they want to recover the energy that is spent there. This is a classical example, otherwise, of a passive system, right, of energy transformation. A dam, you have some water here. There is a difference of level in the water, so there is a difference of potential, right? So there is some potential energy stored due to the difference in the levels of the water, and then when you open the valves and the water flows here, you create a movement, because there is this transformation of energy once more of potential into kinetic. It goes, the story, it goes into a turbine, it makes it turn, etc., and you convert it into electrical energy and so on. So this is just one more example of how you can transform energy, and that's what we want to do essentially when we deal with passivity and passivity-based control. So to study all this in a more formal way, what we do is we need some tools, right? Some definitions and some theorems and so on. So what we are going to do is to start with this energy transformation equation, which recovers all what I have been saying so far. And this energy balance equation, what it says is that the energy that you have available at some time t is the same as the energy that you had at the beginning of your experiment, whenever that beginning was, and minus or the energy that was dissipated, that you lost into heat in the bulb or whatever. And of course, the energy that you have available also depends on the energy that you put into the system, right? So you have some supplied energy for what you had at the beginning and what was dissipated somewhere in the way. If there is no dissipation, well, ideally we can think of that. Of course, in reality, there are no systems that are lossless. You always lose some energy, but mathematically you could say that if you don't have dissipation, then you would have an inequality here, and we would call it a lossless system. Otherwise, this energy balance equation is telling you that in a passive system, you can only recover as much energy as, the maximum energy you can recover from it is, of course, smaller than whatever you supplied into it plus whatever was already there, right? So very, very simple inequality. So in the example of the circuit, we have that we have this energy inequality and this energy balance equation satisfied due to the energy dissipation in the current, right? So one cannot pull out more energy out of a passive circuit than what was fed into it. That's a very clear statement, right? So let's look a little bit closer into circuits. At least that's what people did many decades ago, and came up with this interpretation of passivity of linear systems. There is a whole theory in the frequency domain, but I will not go there. So let's imagine our circuit is an RLC circuit. So it has a resistive and an inductive and a capacitor elements. Each of these systems, each of these elements have a key role in the passivity of the circuit. So first of all, if we apply Kirchhoff's law, we can see that we have this equation here. So the voltage equations law of Kirchhoff, it says that the voltage that you put in the input, it's equals to the voltage to the sum of the voltages in each of the elements, right? So the voltage in the inductor, the voltage in the capacitor, and the voltage that is dissipated in the resistor element, right? So this is the Kirchhoff's law of balance of voltages. If we multiply by the current on both sides, so everywhere, we obtain the power balance equation, right? So you can see the first, you could see it as a force balance equation, and the second one, it's a power balance equation, right? So you are multiplying the current by the voltage. Now, what we are doing here, I said that the current is the output and the voltage is the input, right? So this is, you should see it in a more general way as the product of the input and the output. That's a power balance, gives you a power balance equation. So the power in your circuit is equal to the power dissipated through the resistor element, the power in the capacitor, and the power in the inductor, right? If we integrate that on both sides, so we integrate this on both sides, we put integrals everywhere, we will obtain this, right? So then we have the integral of power. Well, it's energy, right? So we have the energy balance equation that is on the slide. So this is the energy dissipated through the resistive element due to the passage of the current. This is the energy in the inductor, and this is the energy in the capacitor. Now, as you can see, I'm using the letters V and T here to assimilate this part of energy in the inductor as a kinetic energy, right? Because the energy stored in the inductor is considered to be kinetic energy, and the energy in the capacitor is potential energy, right? So it depends on the charges on the circuit. So what we have stored in the capacitor, and so all that is so. This is the dissipated energy, this is potential energy, and this is kinetic energy. Now you have the integral from 0 to t, so that gives you the energy available at any time t, and here we have the energy that was available initially both in the capacitor and the inductor, so to say. And on the other side you have the integral of the input and the output, the product of the input and the output. This is called, this expression here is called sometimes inner product, okay? So the inner product of E and V. And it's written, so this is written sometimes like this. Maybe you have seen it. So that would be just this integral there. Yeah, so this is the energy balance equation. As I said, if we rearrange all these terms, we put this and this guy together. Over here, we will call that available energy at the time t. And these two guys, which come from here and here, that will be the initial energy that was in my circuit. And then this, as I already said, is the dissipated energy, right? And this is what I supplied. I just put it on the other side. I guess there should be a minus there. No, maybe not. No, this one went on the other side and then got a minus side. So this is the energy balance equation, right? So what I can pull out of my circuit at any moment equals what was there in the beginning minus what was dissipated plus what I supplied into my circuit. Very simple. The nice thing about passivity is that, well, basically somehow any system, I would say, probably is passive in some way, right? But it just depends what you mean by passivity. As you have seen everywhere here, we have an input and we have an output. So when we talk about passivity, we just need to be clear. Passivity, what do you mean? From which input to which output? Okay, but then you take basically any system in real life, and there will be somehow some mapping there between some input and some output, and you should have this passivity property. So in engineering, another typical example of a passive system is a pendulum, right? So let's see a little bit about pendula, how this passivity works. So let's say we have this pendulum here with there is some torque applied to it here, and it moves with certain velocity q dot, And then it acquires a position, an angle that we are calling Q with respect to the horizontal axis. You can define it the way you prefer, but I'm doing it this way. And assuming that the mass is right there at all concentrated here, then we have this center of mass there, and the gravitational acceleration acting there. So there is a force applied, and L is the distance from the joint, from the axis of rotation to the center of mass. So the force balance equation for this system, as we saw for the circuit, now the force balance for this system is equal to this, right? So we have mass times acceleration, then we have mgl sine of q, which is the gravitational force, right, due to the gravity that is acting on the mass here, and we have some torque that we are putting in our system to move it, right? So this is a force balance equation. We apply some force, and then there are forces that are natural to our system. One force that comes from kinetic energy, and one force that comes from potential energy. So we have this force balance equation, and we can also compute the energy balance equation. So the energy balance equation will be given by this expression here. It's going to be the addition of kinetic energy and potential energy, right? So quadratic function on the angular velocities, and this term of potential energy. Now the energy balance equation can be obtained as follows. The total time derivative of the energy equation equating the force balance equation is this. Let me recall what I'm doing here. So if we take the derivative on both sides of this equality here, everywhere, right, the derivative of that, we will obtain this equation here. So the derivative of the energy equals q dot times tau. The details are not here, but you can see that actually what we have is that, so the derivative of that, so the derivative of this with respect to t is going to be mgl sine of q, right, times q dot. So when you take the derivative of that, you will obtain, and from the derivative of this, you get m times q dot times q double dot that comes from here. So that's going to be tau minus mgl plus sine of q times q dot. And all that is, yeah, something like that. Yes. Sorry? No. All should be divided by. No, this is fine, right? This is q double dot is, yeah, divided by m, right? Something like that. Anyway, this I think there is a wrong sign there, but the thing is that these should go away with that, and you are left only with this term here. Is there a sign wrong there? Here it's minus, right? Oh, here? Yeah. So yeah. Anyway, normally you should get this. So the thing is that all the nonlinear terms go away, and you only have on one side the derivative of the energy, and on the other side you have q dot that we are going to call output, and you have tau that we are going to call input. Yeah. So we have this energy balance equation once more, as we had before. Current integral of current times voltage equals energy, or the derivative of the energy equals current times voltage in the electrical circuit. Now, if you integrate on both sides of this equation, you get, of course, the energy balance equation, that is here, the available energy equals the initial energy plus the supplied energy. So the supplied energy was supplied through the torque that you injected into your system, right? So this is the external input. If you are trying to control this system, that will be your control input. In this pendulum, as you see, this is an ideal pendulum without friction, which obviously does not exist. But if we add friction, what will happen is that we will recover from the same energy equation. We will recover, this dynamic equation with some damping here. Okay, so this is a friction coefficient that is damping our system, right? So, like if we just let it go, it will go down, and then eventually it will stop oscillating and will just go to the natural equilibrium due to this damping. In the previous example, if you just it's an ideal pendulum that you can just push and it will just keep oscillating forever, or maybe just small oscillations, but of course that does not exist. The energy balance equation for this system with the damping now will be this. So the derivative of the energy equals minus b q dot plus square plus q dot times tau. So once again, the output times the input, the dissipativity term, and the energy, the derivative of the energy. If we integrate that, then we get again this energy balance equation, right? So available energy equals initial energy minus what was lost due to the friction, and of course the supplied energy. So we can get the maximum energy that we can get at any moment. It amounts to maximum the initial energy plus what we supplied into it, right? So the moral of the story is that a passive electric element is a device that does not generate of course quotation, because we know that it's not possible to generate energy but just to transform it. But let's say a passive element is a system that does not generate energy, but it only consumes it. Okay, so at best it doesn't, we don't lose anything, but normally it consumes energy, right? So in electrical circuits theory, we say that the voltage source is an active device, right? It's the one that is injecting energy, actually probably taking it from somewhere else. And a resistance is a passive device, right? Because it is the one that is actually dissipating energy. Passivity is an energy transformation concept. You want to see a system as a black box that is just transforming inputs into outputs, and in that way it's just transforming some kind of energy into some other kind of energy. And in this process there is necessarily some energy that is consumed and probably dissipated. So overall, it's an input-output perspective into analysis of systems. Okay, so we don't care so much about what is inside. When we don't want to use passivity to control the system, of course, we want to look into the model, but we will see how these concepts help to design controllers from a very engineering viewpoint, trying to manipulate this energy. So, but other than that, in this theory, the system is really a black box. And what else do I have here? Since we regard the nature of the inputs and outputs and also the laws of physics, then a passive system may be modeled by a transfer function. So of course there is a lot of theory on passive systems for linear systems using transfer functions, using the frequency in the frequency domain. But we can also but it's way more general, because again it's input output. So in your black box you can have whatever, right? It can be nonlinear, it can be discontinuous, time varying. You don't even basically care what's inside, as long as you just have inputs and outputs, right? So it's really very general theory.